So this lecture will just be on doing some example problems. Okay, now I just wanted to do some examples. And the first example I wanted to do was the quiz that you had to take in that first week. And just to remind you what that question was, it says, in our Frank-Mary system, Mary moving with velocity 6 meters per second relative to Frank observes an object at the point 10, 12. That's the xy in her coordinate system when the time is t equals 3 seconds. Also at that time, she observes its velocity of that object, the u, to be 5 meters per second at 30 degrees above the horizontal. And all the questions were is, what is the x, the y, the u, and the angle that it's going at measured by Frank, right? And here, we're not using Lorentz transformations because this was the first week. We're still using the Galilean transformation. We hadn't learned the Lorentz yet. And so first of all, to get x, we know what we need to get x, and we know what x prime is. We know that v in this problem is the 6 meters per second. We know that x prime is equal to the 10 meters. We know y prime is equal to the 12 meters. We also know that t is equal to the 3 seconds. Remember, t equals t prime in the Galilean transformation. We also know u prime was 5 meters per second. And we know the angle was 30 degrees. This is, I guess I should say theta prime. That's the angle in Mary's frame. Okay, so we want to find x. So what was our equation for the Galilean? It was x equals x prime plus v t prime. Well, if we just plug it in, x prime was 10 plus v, which was just 6, times t, which was just 3. 18 times plus 10, that's just 28. Okay, 28 meters. Okay, so that was the first answer. The second one is, what was y? Well, we know y is equal to y prime in the Galilean transformation. Well, y prime is 12, so the answer is 12 meters. Okay, pretty simple quiz. The next one, what is the speed measured in Frank's system? Well, we first want to get ux. We need to first break up and get ux prime. Ux prime is equal to u prime cosine 30, which is equal to 5 times the cosine of 30, which is the square root of 3 over 2, which is 4.33. 4.33, this is in meters per second. Okay, we can also go ahead and get uy prime. Uy prime is equal to u prime sine 30 degrees, which is 5 times 1/2, which is 2.5 meters per second. And so now to get ux, we need to get the unprime. Ux is just ux prime plus v, which is 4.33 plus v, which we said was 6, 10.33. So there's ux meters per second. Uy is just uy prime. Well, uy prime was 2.5, so this is also 2.5. And then we needed to get the final speed, which is u is just the square root of this squared plus this squared. So it's 10.33 squared plus 2.5 squared. 2.5 squared, and that ended up being 10.62. Okay, and then the last part of this was, what was the angle that Frank sees? Well, the tangent of the angle, theta, is just the y over the x. Uy, which was 2.5, all over ux, which is 10.33. And then so theta, if you plug that in, theta was 13.6 degrees. Okay, so that was the test. I gave you a whole hour to do it. Hopefully it took you nowhere near a whole hour to do it. Okay. This next problem I'm going to do is, here we've got a train going through a tunnel. And it says here, a super high-speed train, right here, speeds through this tunnel. You have a problem similar to that, I think, with the barn. I think you have a ladder in a barn. Super high-speed train speeds through a tunnel at a nice constant speed. The trajectories of both ends of the train and both ends of the tunnel are shown in this diagram. Remember, this blue diagram is the train, which is Mary. She's moving along there. There's her X and there's her CT. And here is the tunnel. It's not moving right here. And here's the trajectory of the left end of the tunnel. Here's the trajectory of the right end of the tunnel. And then the front end of the train, remember, it's going to go parallel to this. The back end of the train is where Mary has her origin. There's the back end of the train. There's the front end of the train right there. Okay, and so what they ask here is, which of the following points, A through J, there's a lot of points here, does the nose of the train emerge from the tunnel? So when it pokes out of the tunnel. So that would be when the nose is right there. Well, there's the nose, and there's the outside edge, so it looks like it's right there at point D. So let me put there, D. So that would. At which point does the tail of the train enter the tunnel? Well, the tail of the train is right here. Where does it enter? It enters, well, there's the beginning of it, so it looks like it enters right there at A. At which point is the tail of the train when the nose emerges from the tunnel in the train frame? Well, this is the train's frame right here. Remember, these are equal times right here. Equal times are going up like this. Well, when the nose is coming out of the end, this point is where the back end of the train is right here. So the back end of the train isn't even hit the tunnel yet right here. It doesn't hit it until up there. And then also that would have been point C. Okay, and now which point is the nose, at which point is the nose of the train when the tail enters the tunnel, in the tunnel frame? Well, when this thing enters, he's right there at A. Where's the other end of the train? Right here. Well, this is the front end, and these are equal times, so it's up there. It's up there at that end. You notice right here that in the tunnel frame, the rear end and the front end of the train make it inside the tunnel right here. So this is, but in the train frame, the tunnel is going to shrink, and you'd say, I never see yourself in there. It's going to look like this right here. It's going to look like, to the train's point of view, the train is going to be like this, train. And here's the beginning of the tunnel right there. When it's something like that. Here's the tunnel. It's going to poke out the end. And then later, the train is going to be like this. The train is going to be like this. You can see right here, when the front end of the train hits there, the back end of the train is still poking out the back end. When the back end of the train gets there, the front end is poking out the front end. So this is similar to the problem that you had to do on the homework with the pole right here. The train says I was never completely inside. us outside say, yes, we're completely inside right here. We saw you completely inside the front and the back right there. Okay. Now let's come over to this. This one is tagging up in baseball. Here we say during a baseball game, a fly ball is hit toward left field along the third base line. So this is all on a straight line. There's along the third base line. The left fielder runs forward toward the third base, and here's a guy on third base right here. He's running to catch the ball right here. And so here he is running. This blue coordinate system is the left fielder. He's out there at a certain position, and this is where, right there, is where he catches the ball. Okay. The left fielder runs toward, catches the ball at point B, right there. The runner on third base tags up and starts off toward home base at point E. So he was at rest, and right at point E, he started to run home. And then here is the umpire. The umpire is just at rest all the time right here. So he's up there like this. Okay, so they just say, at which space-time point, labeled A, B, C, D, E, F, G, or H, is the third base runner when the left fielder catches the ball in the umpire's frame of reference? Well, the umpire's frame of reference is this right here. Remember, he's in the rest right here. And we want to know, is the third base runner when the left fielder catches the ball. So when he catches it, here's where he caught it, and where was the runner? Well, this is all the same time. He was right there at F. So the umpire is going to say, you were right there. So at F. At least that on this diagram, it's at F. What about on the left fielder's point of view? When he catches it, where does he say the runner is? Well, according to him, remember, his equal times, he's running, it's this way. So it's actually this line right here. He's going to say it's D. Well, to him, the runner has already taken off. This is a foul to him because the runner took off right there. In the umpire's frame of reference, has the third base committed a foul? Well, no, because this is where the umpire saw it. This is where the third base runner saw it. He hasn't started running yet. Now, in the left fielder's frame of reference, has the third baseman committed a foul? Yes, because he sees him, when he caught it, he sees him already running. Right here, he says already ran, so he says it's a foul. But if the umpire bases his judgment solely on the chronological order in which he actually sees all this stuff, sees the ball being caught and the runner leaving third base, will he call a foul? Well, where does he see him run? Well, remember, 45 degrees is the light, so this is where the runner actually took off. 45 degrees up, this is where the umpire is going to see him take off. When does he see the left fielder catch the ball? Well, you got to go up 45 degrees, which is way out there. So he's going to see him take off running before he catches the ball. So the umpire is going to say, no, this is a foul right here. It's a foul. He took off running. You can't take off running until after he catches the ball. Okay, so you can see that there's just some of these strange things that happen with the relativity. Okay, the last one I wanted to go over here was this one right here. This one is just two events occur at the same place in Mary's frame and are separated by 4 seconds. What is the spatial separation between these two events in Frank's frame if Frank sees them separated by 6 seconds? So if I were to just draw the picture for it, remember we have a picture right here. And, well, I guess I'll do it all in one color. Right there. And we said that two events occur at the same time, at the same place in Mary's frame. same place would be, these are the same places right here. So let me just pick two spots. There's one spot, there's another spot. So this, in Mary's frame, this would be x1 x1 prime. Let's make this one 1. x1 t1. These would be the primes. And this would be x2 prime ct2 prime. And in Frank's frame, this would just be x1 ct1. And this point right here would be x2 ct2. Okay, so there's just our picture of what's going on right here. So first of all, we can say that since these two events occurred at the same place, two events occurred at the same place in Mary's frame, doesn't that mean that x2 prime and x1 prime are equal? Or x2 prime minus x1 prime equals 0. They both happened at the same time. Also, Mary says the time is separated by 4 seconds. That would mean that t2 prime minus t1 prime is equal to 4 seconds. And Frank says they're separated by 6 seconds. So t2 minus t1 is equal to 6 seconds. Okay, so we've got that right there. So now, suppose we come over here and we say, let's use our transformations, t2 minus t1. Plug in our transformation. We've done it enough. I'm not going to go to the equations. Hopefully you remember. This would be t2 prime plus x2 prime v all over c squared divided by the square root of 1 minus v squared over c squared minus t1 prime, which would be t1 is t1 prime plus x1 prime v over c squared divided by the square root of 1 minus v squared over c squared. Okay, so we can simplify this. First of all, t2 prime minus t1 prime. They both have the same common denominator right here. They both have the square root of 1 minus v squared over c squared. But we got t2 prime minus t1 prime. t2 prime minus t1 prime is just 4 seconds. So we got 4. Then we've got x2 prime minus x1 prime, but they're both the same. So these two terms just cancel out right here. Okay. And this, we know what this side is. T2 minus T1 was 6. Right here, 6. Okay, we need this to get the velocity. We can see that 6 now, let's actually divide it by 4. So 6/4, or 3/2, equals 1 over the square root 1 minus v squared over c squared. Or if we wanted to get the speed out of this, we could square both sides, which would be 9/4 equals 1 over 1 minus v squared over c squared. Flip both sides, so we got 4/9 equals 1 minus v squared over c squared. Bring this over, take that back, so we get v squared over c squared equals 1 minus 4/9, which is 5/9. Or v is equal to the square root of 5 over 3 c. So we needed that because what they wanted us to find is, we want to find what is the spatial separation. We wanted to find x2 minus x1. So x2 minus x1, we'll plug in what x2 was. We'll plug in terms of the primes. What was that? That's x2 prime plus vt2 prime all over the square root 1 minus v squared over c squared minus x1, if we plug in, it's x1 prime plus vt1 prime all over the square root of 1 minus v squared over c squared. Okay, and we got the one common denominator, square root 1 minus v squared over c squared. And then we got x2 prime minus x1 prime. x2 prime minus x1 prime is 0, so that term cancels with that term. And then we get v, we can factor out the v, and we get t2 prime minus t1 prime. t2 prime minus t1 prime is 4 seconds. 4. And then we know what v was. It was right there. It's the square root of 5 over 3c. So this is 4 times square root of 5 over 3c. And then over here we got 1 over the square root of 1 minus v squared over c squared, which is really right here. So I can just multiply it by 3 halves. Multiplied it by 3 halves. The 3's are gone. A 4 and a 2 can cancel down. So this is just 2 square root of 5, 2 square root of 5 c. Right there. Now this doesn't have units of speed because we didn't, this is really a unit of distance right here because this x has a unit of distance right here. So these would all be in meters if I put in the speed of light in meters right there. Okay, so there is 2 square root of 5. I didn't write out what it was, but it'd be that many meters right there. Okay, so again, I'm just calculated this, and I needed to get v first, and they gave me so much of the primes here that I figured I'll get v out of that. And then once I know v, I can go ahead and plug it into this end. Okay, just know how to do these. Hopefully they're not too bad, just algebra. Okay, thank you.